Precipitation reactions take place in aqueous solution. This is a graphic following up the animation on the silver chloride here. Same kind of concept. The only difference is it's using potassium chloride as one of the reactants instead of sodium chloride, but they do the same thing since potassium and sodium are both alkali metals and they're always soluble. So defining the word soluble here, soluble means that it's going to dissolve, it's going to separate in water. We use AQ, that's a symbol in the chemical equation to denote the fact that they separate into their ions. Insoluble is used when the solid does not dissolve in solution. Or we also put S next to it if it precipitates out. So basically, we put the silver nitrate with the potassium chloride together, you'll see silver chloride is precipitating out of solution. However, if you were to take silver chloride and just like dump it in water, it's just going to fall to the bottom and stay a powder. Like it's not going to separate. The dissolution process, water's hydrogen bonding is not strong enough to pull apart that ionic bond between the silver and the chloride. Because that ionic bond is stronger than the water IMFs, that is why it would be insoluble or follow the insolubility part on the solubility rules. Okay? Has to do with the fact that that ionic bond is stronger so it won't separate. Now the ones that are soluble, the ionic bond is weaker and the hydrogen bonding in water can separate it. This example right here, another good particle model diagram showing the precipitation occurring here. So right here, this is when they are initially mixed. And we have barium, we have nitrate, we have potassium, and we have chromate. So different ions here, as you can see represented by them. The nitrates, okay, you would identify them as having the 3 atoms attached to the central atom, NO3. And the chromates have 4, so you'd identify those being separate, okay? As you can see here, the potassium and the nitrates stay floating around in the water. At the bottom, though, the -2 of the chromate attracts to the +2 of the barium. That ionic bond is really strong, stronger than the water, so it falls together and forms this nice precipitate. In this case, it's a light yellow for that particular one. Just showing you another representation here of those particulate model diagrams. Now, solubility rules. I put them all up here for you, and you can Google them at any time, and you'll see very different variations in books and online in tables. Number 1 and number 2 are the ones I say most people should memorize and know. And I made them bold because, obviously, if you know these 2, you can pretty much safely assume everything else is going to be insoluble or will precipitate out. All alkali metal salts and ammonium, okay? Those ones are always soluble. It doesn't matter what they're with. If it's in there, that compound's always soluble. Nitrates, chlorates, perchlorates, and acetates. Now, acetate, you might remember, was written like this last year in Chem 1. However, you'll see it written in the organic form, CH3COO-, more often in AP because they like to do it in the organic form and show it in that particular way. So all of those are always soluble too. Now, if you know the ones that are always soluble, then you can pretty much safely assume the ones that are not. If they don't fall into those 2 rules or have one component of those 2, then it's going to be insoluble. Now, officially what AP says that you have to memorize, although last year there was sort of a question about it on the FRQ because they gave a perchlorate one, and that's not in this SNAP. They call it SNAP. They say you should know that compounds with sodium, compounds with nitrate, compounds with ammonium, and compounds with potassium are always soluble. So I feel like that was kind of a sticky point because a lot of people will put silver precipitating with the perchlorate because, they assumed it would be insoluble. So I would know 1 and 2 just for covering all your bases. But this is what AP says that you have to know. Sodium, potassium, ammonium, and nitrate. Those ones are always soluble. So let's take a look here and practice reading our solubility rules, which the following ions form compounds with lead that are generally soluble in water. Okay, so for reading our rules here, sulfides, which is S-2, sulfides, are those typically soluble or insoluble? Insoluble, so I'm going to say no to that one. How about chlorides? Soluble or insoluble? Chlorides are typically soluble, but there are 3 notable exceptions. What are the notable exceptions? Silver, mercury, lead. So in this case, would chloride work with lead? No. Notable exception there. Now, nitrate. Yes, nitrate's always soluble. Doesn't matter what it's with. Check, check. Sulfate. Sulfates have a lot of exceptions. They're typically soluble. However, with lead is one of the notable exceptions. So that's a no. And would lead form a compound with sodium?
No.
No. Why would a cation form a compound with another cation? What do positively charged things do to one another?
They repel.
Yes, they repel. So that one doesn't make sense at all. Very good. All right, so the only one there that would remain soluble out of any of those would be nitrate. All right, so still practicing reading the solubility rules, and I have you do this because in the textbook questions on Mastering Chem, they don't really care what the AP rules are. They want you to be able to read all the rules and figure it out. So I gave you a couple combos here. All right, when using solubility rules, predict if a precipitate will form when the following pairs of solutions are mixed. So this is a compound plus a compound. What type of reaction occurring here? Double replacement. So what you need to do in the double replacement, the K is going to go with the Cl, right? The cation of the first one goes with the anion of the second. And the nitrate, the anion of the first goes with the cation of the second. So those are the kind of how you want to construct it in order to say, oh, would barium nitrate or potassium chloride work here? Okay? And based off of looking at, if I put potassium with chloride, get KCl, and then barium nitrate, BaNO3, Now, you do need to kind of get back into ion writing. And we know that potassium is in group 1, so its charge is +1. We know nitrate, if you look at the table, or if you don't remember nitrate, I put lots of the polyatomic tables at the end of the notes so you can refer to them and get familiar with them. But nitrate is one you really should know off the top of your head. They use it all the time. What is the charge on nitrate? And even if you didn't know nitrate, if you knew that potassium's +1, which you should because it's an alkali metal, because it's 1-to-1, you know the nitrate's charge is -1. They have to add up to 0. Don't forget, the charges in an ionic compound have to add up to 0. So that also brings us to the barium chloride. Barium's in which group? It's in group 2, alkaline earth metals. Very good. So what's its charge always going to be? +2. And chloride, ionic compound form here, halogens, when they're ions, what charge do they have? -1. Okay, that makes sense because you need 2 chlorides to balance out the +2 there, so it adds up to 0. So think about that as you're figuring out these compounds, and then look at your solubility rules. So if we're looking at our solubility rules, KCl, is that soluble or insoluble? Okay, so that one's soluble. How about barium nitrate? Soluble. So do we have a precipitate here? No, so this is a no reaction. And sometimes you have a no reaction. They all just float around in the water and they don't actually form a bond and you don't get a precipitate out of it. But look at B and C, try them real quick. See what you get. Take a look at B and C. So, sodium goes with nitrate. Sodium's +1. It's alkali metal as well. Nitrate we know is -1. The other one here, combining the sulfate with the lead. What's sulfate's charge? -2. And the lead here, because it's a 2, so this is going to be +2. So you get PbSO4 as your other possible product. So, sodium nitrate, soluble, insoluble? That one's soluble, lead sulfate, lead 2 sulfate. This one is insoluble, so this is the one that's going to precipitate. Okay? That's going to fall to the bottom as powder. Now here, looking at, we have potassium going with nitrate, so KNO3. And then this, now what is the charge in the iron? Iron's one of those transition metals that can have multiple states. It's 3. We know this because nitrate is -1, and if there's 3 of them, that has to be +3. Very good. So this combines with hydroxide. What's hydroxide's charge? -1. So that's going to be FeOH3. Now, our hydroxides, we already know this, that's soluble, has the alkali metal and the nitrate, so it's kind of got both those rules in there. But the iron 3 hydroxide, are hydroxides typically soluble? No. Okay. So this one's going to precipitate. It's actually going to be kind of an orangey precipitation, or light brown, because that's what iron does. So we would get iron 3 hydroxide as the precipitate. Yes.
Sorry. For letter B, when we combine sodium and nitrate, where did the 2 go for sodium?
Well, remember the writing of the formula for ionic compounds isn't about the original subscripts, it's about the charges. So sodium's +1,
Okay.
nitrate's -1. So you need one of each to make it out up to 0. The +1, -1 cancel out and you get a neutral charge of 0 on the compound.
Okay.
So the subscripts don't necessarily transfer. It's always writing ionic compounds is based off of the charges.
Okay.
And you get the right ratio by figuring out how, each one adds up to 0.
Got it. And then lead and
So lead's +2, sulfate's -2, and so you just need one of each, it adds up to 0.
okay. Got it. Thank you.
Okay. Good question. All right, there we go. Now, formula or molecular equation. This is what you think of as a normal balanced chemical reaction. We use it for stoichiometry, okay? When we're doing our mole ratios and things like that. So this is your regular balanced equation. So for instance, for example, here we have silver nitrate reacting with sodium chloride. This is the one you saw in the simulation. Produces our precipitate, silver chloride. And we have sodium nitrate, still aqueous, floating around in the water. All right, regular. Everything in this one is 1 to 1 to 1. It's all balanced. Okay. They're generally shown as compounds, like I said, the regular chemical reaction here. And you just use the solubility rules to figure out if you have a precipitate forming or not. In this case, solubility rules would say yes, chlorides are generally soluble except for with silver, lead, and mercury. And we have silver here, so that one's going to precipitate out. Now, complete ionic equations are a little bit different. This is one showing them in their ionic form. So all substances that are strong electrolytes are represented as ions. Strong electrolytes, of course, are ones that are in ionic form in the water, separated. They can conduct electricity. So strong electrolytes, they have the charges, they can conduct the electricity. That's because they're separated and in their ion form. So if you're looking back at the original equation, if you go back to our regular formula, molecular one for our silver nitrate and our sodium chloride, what you'll notice is anything that has an AQ next to it, which means it's dissolved in water, so that means the ions are separated. Anything with an AQ next to it has to be separated into ions. And brings us back to the idea that you have to know the charges to separate them into their ions and make sure that it's balanced. So if we're looking here, the silver nitrate, +1, -1, those separated because they had AQ next to them. Sodium and chloride separated, +1, -1, because of that's what their charges are. Sodium's alkali metal, chloride's halogen. And silver is one of those random transition metals, by the way, and this is on the list in the back of your packet there. Silver is always +1. It is not a multiple oxidation metal. It will never have a Roman numeral. The only charge it ever has is +1. So that's sort of a memory thing. Remember, zinc is the other one that's really important. Zinc's always +2. The rest of them in that section, though, they could have varying oxidation states or charges. So on the product side, we know that the silver chloride here formed a precipitate. That still stays together. It's a solid. It's bonded. It fell to the bottom. But the other substances, which happen to be the sodium and the nitrate, they're still floating around in the water, haven't done anything. So they stay in their ion form because they also have this AQ next to them. So notice the AQ next to them means you separate it into the ions. Sodium still +1, nitrate still -1. This is a 1-to-1-to-1. This is a pretty easy one to do. Okay, so that's the complete ionic. And there's one of the problems that where you're going to have to break everything up into the complete ionic, and then we do the net ionic equation. And the net ionic equation only shows what's actually reacting. Okay, whatever is in there that's not reacting is taken out of the equation. So if we're looking at this particular reaction, the silver forms a bond with the chloride, and now you get the solid precipitate at the bottom. Those are really the only thing reacting. The other components just floating around in the water. And the ones that do not react, we call them spectator ions. They're basically watching the show like spectators do at a sporting event, but they're not actually in the play. They're just watching. So in this case, like if we're using the sports analogy, the players would be the silver and the chloride. They're the ones that are participating in the event. The sodium and the nitrate are spectators. They're just watching the reaction occur. All right. So, little review, back to naming, and mainly for right now, this part, although you will be able to use some of the other stuff later on when we get to more of the molecular stuff. But you want to pay attention if you don't remember naming. This part of the chart, that's the ionic part. Okay, metal or ammonium, if those are the cations. Basically, first element, is it a mom, a multiple oxidation metal? If it's a mom, yes, you need the Roman numeral. If it's not a mom, you just write the element and the IDE ending on the non-metal. So it's basically metal, non-metal, unless you have polyatomic ions in there like ammonium. Covalent is the prefix system. Like I said, we're not going to concentrate too much on that. You also might need to recall the acid naming. Acid naming, monatomic, without oxygen, it's the hydro something ic. I don't know if you guys, some of you remember my ride has hydraulics, you can use that. The IDE goes with the ic, hydro something ic. If it has oxygen, because it's a polyatomic ion, if it's an 8 ending, I ate something icky, you just change it to ic. And if you have the ite ending, okay, the ite versus the 8, ite, Sprite is delicious, you just change it to OUS. Okay, like nitrate, if you add an H on it, it becomes nitric acid. Nitrite, though, if you add an H on it, becomes nitrous acid. And if you just add nitride in, which is N-3, it's hydronitric acid. Okay, so go back over that. You can take a look at some of that. You might need it. I don't know. I'm throwing it back in there as a review for anybody who wants to. There's also videos from last year in Chem 1 on the Mastering Chem Summer Enrichment slides that you can go to if you need to, refresh on the naming stuff. This is one of the charts that I put in the back of these notes, and that's why I said you have cations, you have polyatomics and anions on here, and the selected transition metals that have multiple oxidation states. So group 1 alkali metals, +1, group 2, +2, 13 is +3, that's like aluminum. Group 14 is usually +4, although tin and lead do +2, +4, so they are in the multiple oxidation realm. The polyatomic cations are basically ammonium and hydronium. Hydronium is that one's gonna pop up a lot in acids and bases. Here's your selected transition metals. Oh yeah, don't forget silver, zinc. They only have one oxidation state. Silver's +1, zinc is +2. And then here for the simple anions, the IDE ending, group 17, the halogens, -1. If it's oxygen group, it's -2. If it's nitrogen group, it's -3. There is an occasional one for group 14, but most of the elements in group 14 do covalent bonding rather than ionic. So, organic polyatomic ions, acetate, oxalate. And when we did an example problem with oxalic acid for the molecular stuff, but it's C2O4 -2. And then here's common polyatomic ions. like I said, they don't expect you to really memorize all of these, but if they give you a formula, something like, MnSO42, like that, they expect you to be able to figure out, well, actually, no, because that would be sulfate. Let me think of something else. How about this one? Al2SO43. They expect you to know aluminum is +3. So from that, you should be able to figure out the charge on the SO4, which is -2. Okay, because it's the common multiple idea, so it should be +6 -6 adds up to 0. So that would be one that they would be able to expect you to be able to separate. Transition metals, they probably have to write it down for you and say, this is manganese 4 sulfate, and then you could figure out +4 and -2. Permanganate we'll be using when we do redox. So some of these will pop up at varying times. That's why I gave you a list of them, so you can always go back and refer to them. This is the list I give out in honors for Chem 1. So you can compare it to the previous list, but it also has a bunch on there. Some of them repeat, some of them don't. So just definitely take a look. Be familiar, start relearning them. There are some that I would say, like, you should just know. Here, I'll circle them. Nitrate, you should just know. Hydroxide, you should just know. Chlorate.
Ammonium, right?
Ammonium, yes. That one is on there. Phosphate. Where's carbonate? Carbonate. Sulfate. These are basically the ones you have to know for the SOL for chem, regular, Chem 1 stuff. So these are ones they just think that you automatically should just know. So you might want to circle those and make sure that you become familiar with those. Those ones will pop up more frequently than others, but, you have the charts to refer to. I would have this out when you're doing your problem set. It will be really helpful. So you won't have to go individually looking stuff up. Because now we're going to start writing molecular equations, complete ionic, and net ionic equations. So, first example here, I'm going to work this one through, and then you're going to try a few on your own. So, See here in the problem, the way it's written, they tell us this is cobalt 2 chloride. They give you the formula here, right? Based off of both of those pieces of information, you should be able to figure out the charges, right? So this would be CO would be +2, and this is -1 kind of idea here. Now, for the formula or molecular equation, basically starting out with our two reactants here. And they tell us, right, that, okay, so we're reacting here. Write the correct molecular, complete ionic, and net ionic equation for these solutions. And if you look on your solubility rules, you'll notice that this one would be AQ because chlorides are generally soluble except for silver, mercury, lead. Cobalt's not one of those. And sodium hydroxide, anything with sodium is always what? Soluble. So this would be also AQ. So you can denote that. Put an AQ here, AQ here. Now for the double replacement part. Cobalt's going to go with what? Cobalt's going to go with hydroxide. And cobalt's charge is +2. What do we know about hydroxide? -1. So we need 2 hydroxides. COOH2. That means you have to have the parentheses, keep the hydroxide group together. All right. And what's our other product going to be? Sodium goes with the chlorine, yes. And sodium is +1, chlorine is -1, or chloride is -1. So there you go. Now we have to figure out what these things are. Are they soluble, insoluble? What symbols to put next to them? I think we all know NaCl is going to be what? Yeah, that one dissolves. We know that one off the top of our head because we know of oceans.
It's not salt. Oh.
Yes, oceans have lots of salt in them, so therefore always soluble. Now let's look at what are hydroxides. Generally insoluble. And does cobalt take priority with, like, no, there is no cobalt rule, so there's no exception there. This one's going to precipitate out and become the solid. The only hydroxides that would be soluble are alkali metals and ammonium. Okay? All right, now that we have our general construct, our molecular equation, what should we do next? Balance it. Let's balance it because it's not in balance. What needs a number? Two. What else needs a number? 2. Very good. All right, so we balanced it. Yay. Now we can do the complete ionic. So which ones do I break apart again? All the ones that are aqueous. So the cobalt 2 chloride here, I'm going to break apart. CO2 plus, you have to write it in ion form, so put the charge in the upper right corner. And technically you would write AQ out each time, but you don't have to do that because it's very time consuming. Although actually I think they do make you type that in Mastering Chem. So I'll do it here. Now the difference is when this formula unit breaks apart, we get 1 cobalt, but how many chlorides do we get? 2. When it breaks apart and separates, there's always going to dump 2 chlorides out of it. So we have to balance that. So we're going to get 2 chlorides. Okay? So every time that one thing separates, 1 cobalt, 2 chlorides. Now for the sodium hydroxide. When these guys separate, it's 1 to 1, but how many are needed in the reaction? 2, so you still have to balance that out too. Na plus and 2 hydroxides. The first one on the other side is very easy, because guess what? It has a solid here, so do we separate it? No, we leave that one together and nice and intact. And last but not least over here, this is going to break apart, and we need to keep the balancing in. So we get 2 sodiums plus 2 chlorides. Now, a good way to approach these when you're trying to figure out the net ionic from the complete ionic is look for the spectator ions. And to be able to identify the spectators, there will be an ion form on both sides of the arrow. So which ones are in ion form on both sides of the arrow? We have sodium and we have chloride. And we have sodium and we have chloride. They are on both sides. So these are our spectator ions. So they should not appear in our net ionic. So basically, those cancel out. And our net ionic equation will just be the cobalt plus the 2 hydroxides. That's going to give us the cobalt 2 hydroxide solid. Now this is why these problems are very long, because you have to do the complete ionic and then go to the net, cancel out, or mentally cancel out your spectators to write your net ionic equation. So now it's your turn to practice. I gave you 2 example problems to try. One is potassium chloride with silver nitrate. The other one is potassium hydroxide with iron 3 nitrate to start out. So those 2 give you about 10 minutes to work on that. Ready, set, go. All right, so let's take a look here. Check your answers. The first one's pretty easy because everything is 1 to 1 to 1 because it's +1 -1 for both the ions in each compound. So as you can see here, the silver chloride is what precipitates. The potassium chloride the potassium and the nitrate, are the spectators. So they're the ones that get taken out and are not written in the net ionic equation. This one's easy because everything's 1 to 1 to 1. The next one, though, was not 1 to 1 to 1. So you have to remember to originally balance the molecular formula equation before you start doing anything else, because you need 3 potassium hydroxides, 1 iron 3 nitrate, and you'll get your iron 3 hydroxide and 3 of the potassium nitrates. Once again, you see here the ones that are spectating happen to be the potassium and the nitrate. The hydroxide and the iron ions are the ones that are actually forming a bond and creating the precipitate of iron 3 hydroxide. So, not too bad, but you'll have some practice, like I said, and expect to have, on the quiz, you'll expect to have 1 balancing. I'll probably give you the molecular up front, you balance it, then you have to do the complete ionic and the net ionic from it. So do expect 1 of those on the quiz. All right? Now, exercise 5 is a little bit of a wrinkle in comparison to what we've been doing. Still takes place aqueous solution. This one happens to be a single replacement though. We have zinc metal, so that's element, added to hydrochloric acid, compound, rapid production of hydrogen gas, okay, occurs. So, first thing you should do is figure out the balanced overall molecular equation. Add zinc metal, what phase of matter would zinc metal be in? Solid, right? Adding it to hydrochloric acid. Hydrochloric acid is designated as what type of matter?
Aqueous.
It's aqueous because the acid is actually dissolved in water. So acids will always say AQ next to them. Now over here it tells us one of the products, which is hydrogen gas, H2. So what do I put next to my H2? G. Now, doesn't tell you the other product, but you can figure it out very easily. What is our other product? Zinc must pair up with the chloride here. Now we have to go to charges. What's zinc's charge?
2.
Plus 2. What's chloride going to be? -1. So if we're writing the formula correctly, it's got to be ZnCl2. Now we go to our solubility rules. Chlorides are typically soluble, except for with silver, mercury, or lead. Zinc doesn't happen to be one of them. So guess what this is? Aqueous. There you go. Now we need to balance. Are we balanced? No. What do we need? 2 right there. All right, so overall ionic equation or complete ionic equation, there's only 2 things that we have to break apart up here into ions. Which 2 have to be broken apart into ions? These 2 have to be broken up into ions, okay? The zinc is a solid. Anything that's not AQ just stays what it is, so keep the zinc solid here. Now we break this apart into its ion. What is the H going to be if it's in an acid always? H plus. There you go. And there's 2 of them, so 2H plus, AQ, plus 2 chlorides, AQ. Now, hydrogen is a gas, so we have to leave that alone. Can't touch it. Okay, and we break this apart. We get zinc. Now, what's the charge on the zinc again? 2 plus, good. That's AQ. And we get 2 chlorides out of that. Because remember, every time this breaks apart, you get 1 zinc and 2 chlorides. 4 there. Yes?
Would you put the 2 in front of the H instead of just having H2?
No, because this is hydrogen gas. It's elemental hydrogen just going up into the air. So, remember, elemental hydrogen is one of the diatomics. So, you have to write it as H2. So, that goes for, say it said chlorine gas, it would be Cl2. Or if it was fluorine gas, it'd be F2. Any of the diatomics, when they are by themselves, they're the twins. Yes?
So when there's a piece of the equation that's a solid, we don't have to write the charge.
Correct. If it's a solid, or if it's zinc metal, that means it's elemental zinc. So that means that it is 0 charge.
Oh.
Anything elemental has a charge of 0 because it has not reacted with anything yet. Yes.
So when you're changing it into an ion, so anything that has a subscript, you would put it to the front?
Well, think about it in terms of this zinc chloride crystal. You dissolve it. When it separates, every time it separates, you get 1 zinc, but you're going to get 2 chlorides. So that's why the 2 goes in front, because every time this breaks apart, you get 1 of those, 2 of those. So it's just, yes. Yes, you would take if it's AQ, you would take the subscript and put it in front, yes.
Thank you.
But it really is a matter of this is what it's going to form. All right. Yes.
How did you find the charge of zinc?
It's on the list, and that's just one you have to memorize. Remember, silver's +1, zinc's +2. Out of the transition metals, those ones are not multiple oxidation metals. Cadmium's one of them, but that one's not as important. Zinc and silver are very important. It was important last year, but yes, this year we're going with zinc and silver. Okay? Now, identify the spectators. Which ones are our spectators? In ion form on both sides of the equation to be a spectator.
2CO.
So chloride is the only one because it's in ion form on both sides. Guess what? Zinc is in solid form on this side. It's in ion form on the other. That does not count. That is not a spectator. And hydrogen, although AQ here, it is not. It's gas on the other side. So that one is not a spectator. It is actually reacting. So the net ionic then will consist of everything but the chlorides. So zinc plus the 2 hydrogens is going to give us the hydrogen gas plus the zinc ion. these single replacements look. The single replacements, basically, when we do it this way and we cut it out and get to the net ionic, now it really turns into a redox. And we will get to redox later in here, but for those that remember redox from last year, this would be 0. These are +1s, that is 0. This is +2. So you can easily see that the zinc is going from 0 to +2, it's being oxidized. The hydrogen's going from +1 to 0, it's being reduced. So, like I said, we will be doing an entire set of notes on redox again. So if you're like, what does that mean? We're gonna cover it in detail.
So zinc is a reducing agent?
In that particular case, zinc would be a reducing agent, yes. But you don't have to know the agents this year, so.
What?
I know, right?
It's like
You're
the
gonna
only
like
thing I
that, okay.
remember.
Now let's talk about physical changes real quick. Writing equations with physical changes. Dissolution of soluble ionic salts. What does that look like? Balanced chemical equation, it's just the solid going to the AQ. Solid means it's together as a solid, AQ means it's dissolved in the water. However, we want the net ionic. We would separate our ions, right, because they're AQ. In this case, for that formula unit of calcium chloride, you'd have 1 calcium for every 2 chlorides. So you'd break it apart, and you'd have the 2 in front of the chlorides. So this is just showing the dissolution of calcium chloride. The top one being like the regular molecular equation, the bottom one being the net ionic, showing everything that's taking place. The next one would be the dissolution of molecular solids. Do molecular solids separate?
No.
No. So guess what? They stay together. Formula stays together, doesn't break apart. So if I'm dissolving sugar in water, which basically that's sucrose right there, which is table sugar, it's going to go from solid to AQ. The water's just going to surround the big entire molecule, does not separate. So the net ionic is going to be the same because there is no separation occurring. So those are one and the same.
Why doesn't it break apart?
Because it's molecular. It is not for ions. It is all covalently bonded, sharing electrons. They don't break apart. Yes.
How do you know that?
How do I know it's molecular? Because everything in there is a nonmetal. When everything's nonmetal and there's no polyatomic ions, it's going to be molecular.
Got it.
All right, phase changes. We kind of talked about phase changes in a previous one, but let's look at my first example. Phase changes can be written for the melting of substances, like the melting of sugar. And if you've ever melted sugar, you'll notice, obviously, if you put the heat up too high, it's going to turn a little brown. But get a nice glaze going. Doesn't take a lot of heat. Molecular solids don't have very high melting points anyways. And the deposition of iodine here, as you can see the purple gas, that's iodine. You can see it depositing, going from gas to solid. Those are those silver crystals on the bottom of here, because the ice and you have like ice on top here, and it is causing it to cool down, so the gas deposits into solid. So at the bottom here, it's actually subliming first into the gas because it's warm enough down there, and then when it gets up here to the ice, it deposits. So that's kind of cool, but it is a pretty pink, purpley gas. It's one of the few that actually has color. So, exercise 6, pretty easy stuff here. Write out the chemical equations for the net ionic for the following physical changes. Obviously, you see A is one of those dissolution of a soluble salt because it has potassium in it, and potassium is always soluble because it's alkali metal. Snowflakes forming water vapor, and then the dissolution of ascorbic acid, which is vitamin C in water. So yes, they're all nonmetals, and you see them as carbon, hydrogen, oxygens. You know, definitely going to fall under that molecular solids umbrella. Let's go ahead and take a moment, write those out, and we'll check them. Okay, so let's take a look, see how you did. First one, potassium phosphate stays together, but it's solid to AQ. Then you have to break it apart, but you need 3 potassiums for the balancing. Okay? Snowflakes forming water vapor. That's sublimation, so these should be solid to gas. Water vapor is the gaseous form of H2O. And here, dissolution of ascorbic acid really only has the one reaction because the net is the same as the formula equation because it's molecular, so it's not going to break apart.
This is insane.